Next up is Troy Lee.
Okay, so I'm going to talk about joint work with Dmitry Gavinsky, Miklos Senta, and Swagato Sanyal. So actually, Swagato and the three of us independently proved the lower bound that I'm going to talk about. So if you go and look for this paper on the archive, you're actually going to see two papers. But since we've merged the two papers, and we have a joint write-up, but we haven't put it on the archive yet, so it should be there eventually. Okay, so we're going to talk about function composition. So imagine you have two Boolean functions. G can be a partial function. And we look at it, I think, a very natural operation, which is the composition of f and g. Okay, so we can take n strings, x1 through xn, which are in the domain of g. We evaluate g on each of these n strings, g of x1 through g of xn. That gives us an n-bit string. Then we feed this n-bit string to f and look at the evaluation of f on that. Okay, so pictorially, you can kind of view it as a two-level circuit here, with the top gate is f, the bottom gates are g's. The input to g are these n-bit strings here. We feed those into g and then feed the results into f. Okay, so I think a very natural question for people in this audience is, how does the complexity of f composed with g relate to the individual complexities of f and g? And this is a question that you can study for many, many different complexity measures. So, say we have a general complexity measure m. Kind of what you expect from a complexity measure is that it's submultiplicative. Okay, so the complexity of f composed with g is at most the complexity of f times the complexity of g. So, this is true for most complexity measures, not all. But usually if this is true, it's not going to be difficult to prove. So the other direction, on the other hand, which would be a lower bound on the complexity of f composed with g in terms of the complexities of f and g, that can be quite difficult to prove, and that's what we refer to as a composition theorem. So there's many composition theorems that have been proven. I decided to just select a few from people who I thought would be in the audience. So for example, approximate polynomial degree is a nice example because it shows that even for specific f and g, so here if you just want to know what is the approximate polynomial degree of and composed with or, this can already be a very difficult question. Okay, so there was a long line of work improving lower bounds on the polynomial degree of and composed with or, until recently Scherstoff and Bunn-Thaler came up with a tight lower bound. And it's kind of what you expect, right? It's the product of the approximate degrees of the or and and. Another one, since this is communication complexity workshop, I thought I'd mention lifting theorems. So you can kind of also view this as a kind of composition theorem, although here the setting's a little bit different because you're composing two different kinds of objects. So here f is like a query function, g is a communication gadget, and what you try to show is that the communication complexity of f composed with g is at least the query complexity of f times the communication complexity of g. And this has now been successfully done for quite a few different kinds of communication complexities and their associated query measures. So for example, Guzpatasi and Watson have done this for deterministic and randomized communication complexities. So finally, I want to point out this work of Gilmer, Sachs, Srinivasan, and Tall, who study composition for a lot of different Boolean function complexity measures like certificate complexity, block sensitivity. So block sensitivity actually turns out to be one that doesn't have this multiplicative property. So that's quite interesting. Okay, so those are some examples of different kinds of composition theorems in the literature. We're going to focus on query complexity. Okay, so let me talk about some composition theorems that are known for query complexity. So start off with the deterministic case. So it's very easy to see that the deterministic query complexity is submultiplicative, right? So if you want an algorithm for f composed with g, you just run an algorithm for f. Whenever that f makes a query, then you go ahead and run an algorithm for G in order to answer that query, and then you keep going like that. So Montanaro and Tal, in 2 different papers, showed that this is actually tight. Okay, so for deterministic query complexity, we really have a perfect composition theorem. The complexity of F composed with G really is exactly the product of the complexities of F and G. So for quantum query complexity, we also have a composition theorem. This time it's tight up to a multiplicative constant factor. And I think it's actually interesting. Actually, the quantum case was even proved before the deterministic case. Okay. But of the kind of 3 main query complexities, deterministic, quantum, and randomized, randomized is the one that is still left open. Okay. So again, the easy direction holds, with this extra log factor, but it's still open what the lower bound is. Okay. Yeah.
Quick question: are the quantifiers on FNG for all FG, or there exists for the hard direction?
For the hard direction, then you'd want for all F and G.
For all.
Yeah. But again, I mean, you can also show it for specific F and G, and like the case of polynomial degree of and composed with or, that can already be interesting. Okay, so what's known about the lower bound? So Ben David and Kotari show the following lower bound. So the randomized complexity of F composed with G is at least the randomized complexity of F times the square root of the randomized complexity of G. Okay. And they show this for any partial function F and total function G. So this square root is kind of strange, right? It's not what you would expect to see there. So we actually show an example where F is a relation, so we allow something more general, and G is a partial function, where in fact this square root is needed. Okay? So we give an example of a relation F and a partial function G, such that the randomized complexity of F composed with G really is at most the randomized complexity of F times the square root of the randomized complexity of G. Okay? And we show that this is tight, even in this more general situation, right, where F can be a relation and G is a partial function. Okay, so let me make a couple remarks at this stage. So you might wonder, why am I carrying around these different error bounds? So once you go and talk about relations, then it's not obvious that you can always amplify the success probability, right? You can't just do the thing of repeat the algorithm several times and take a majority vote, because with a relation, your algorithm could be outputting a different correct answer every time. So we have to carry around these error bounds. And also, really, I think the important thing for the lower bound is that G is a partial function. Okay, so that's really the interesting thing for the lower bound. I think that Robin and Shalev, they weren't interested in relations, but probably their proof could carry through for relations. But the bottleneck for them would be the fact that G is total. Okay, so kind of I think the innovation in our lower bound is that it works for these partial functions G. Okay, so I'm going to describe this example. So I think this I can fully describe the example, and hopefully this is something that you can really onboard into your brain. The lower bound I'm just going to talk about at a very high level. Okay, so let's first talk about the example. Okay, so F is a relation. It's a subset of its pairs of n-bit strings, and it's defined in the following way. So in the relation are pairs of strings x comma a, where the Hamming distance between x and a is at most n over 2 minus square root of n. Okay, and again, what is the setup here? X is the unknown string. We're making queries to x, and the question is, how many queries do we have to make to x in order to output some n-bit string a, such that a and x are close? Right, they agree in at least n over 2 plus root n positions. Okay, so the randomized query complexity of this relation is like root n. Okay, so basically, for the upper bound, you can just query the first, 100 times root n bits of x, and then randomly complete that. you know, just randomly choose 0, 1 to complete that to an n-bit string A, and you know, with decent probability you'll be correct. For the lower bound, so for the lower bound we can use what Joshua also mentioned, this minimax theorem. So randomized query complexity is equivalent to looking at deterministic distributional complexity. So just think about a deterministic algorithm which is computing this relation under the uniform distribution. And say that you only make, you know, root n over 10 mini queries, right? So now this algorithm is going to partition the input space into subcubes, right? Subcubes are basically sets of strings that are consistent with some 0, 1 star assignment, okay? So now just imagine a subcube, you know, say a subcube where the first root n over 10 bits, you know, are fixed to be 0, and the rest of the bits can be whatever you want. Now, if you look at a subcube that is, you know, this large, right? I mean, there's like 2 to the n minus 0.1 root n many strings in this subcube. There's basically no good A that you can output on this subcube, right? Any A that you output is going to be wrong on more than half of the strings in the subcube. Okay, so that's basically how you show a lower bound of omega root n as well. Okay, so this is the outer relation F. Now let's talk about the inner function G. Okay, so look here first. So g of x is going to be a partial function. You should output 0 if the Hamming weight of the input is less than n over 2 minus root n, and output 1 if the Hamming weight is more than n over 2 plus root n. Okay? And we claim that the complexity of this g is theta of n. Okay, so the lower bound is actually taken care of for us, again, by a connection to communication complexity. Okay, so the gap Hamming distance communication problem, right, is the problem where Alice has x, Bob has y, and the question is the Hamming distance between x and y bigger than n over 2 plus root n or less than n over 2 minus root n? So you can see that that function is actually just our g here of the XOR of x and y. Okay. So now Chakrabarty and Regev showed that the communication complexity of this function is omega n. So that means that the query complexity of g also has to be omega n, right? If it wasn't, then that would give you a communication algorithm to compute the gap Hamming problem. Okay, so this lower bound follows pretty easily from this communication complexity result. Yeah?
So all you need is that the simultaneous randomized communication complexity is omega n, right?
Simultaneous. No, I mean, because the algorithm for G can be adaptive, right, in the query model. So that could lead to an adaptive communication
I see.
protocol.
Right.
Yeah.
Scratch that.
Okay, yeah. Okay, so now we're going to get, so that's F and G. Now we're going to get into the protocol for F composed with G. So before that, let's just make one observation about G. And that's that although to compute G with bounded error requires like n many queries, if you only want to compute G with a slight advantage over a half, like say advantage 10 over root n, you can actually do that with just a constant number of queries. Okay? And the reason for that is that just query one random bit of the input. That's already correlated with the with g of x, right, with the function value. So if we just sample like 100 bits at random of the input, we can boost this success probability to say have advantage, something like 10 over root n over random guessing. Okay, so that's going to be very important for our example. Okay, we're kind of playing with the error. Okay, so although G is hard, with bounded error, if you only want, like advantage, something 1 over root n over random guessing, you can do that with just constant many queries. Okay, so here's our protocol. So again, what's our goal? So we're given, so there's some input x1 through xn. that we're making queries to, and our goal is to produce something close in Hamming distance to g of x1 through g of xn. Okay, so what are we going to do? Okay, so for each I from 1 to n, we're going to query 100 random bits of xi. Okay, we're going to take the majority, and we're going to set ai equal to that. And then we're going to output that a. Okay? So with probability, something like a half plus 10 over root n, each ai is going to agree with g of xi. Okay? So therefore, if we look at this string a as a whole, with high probability, it's going to agree with x and at least n over 2 plus root n many positions. Okay? Does that make sense? Okay, so that's the protocol. So how many queries did we make? Well, we just made order n many queries, right? We made like 100 queries into each xi. Okay, so we made like order of n many queries. On the other hand, the complexity of the outer relation f is root n. The complexity of g is n. So kind of the naive composition would give you n to the 3 halves. Okay. For this problem, this bound, right, complexity of f times square root of complexity of g is actually tight. Okay, and I think it's important to note, again, how we played with the error here, right? So kind of the naive algorithm would just be to choose root n many positions and spend n many queries into those x to get bounded error. But we played with the fact that actually if you only want a very small advantage over random guessing, then this G has a very easy protocol, right? Just constant many queries.
So
yeah,
why 4/9? I mean, you explained it early on, but I don't see where
well
the 4/9 actually came into the.
Yeah, I mean here it's, to be honest, for this particular relation, it's irrelevant. Because this relation, you can amplify success probability, right? So yeah, I could say 1/3, 1/3. In the upper bound, I could get r of 1/3 if I wanted to, right? But for a general f relation, I don't know how r 4/9 relates to r 1/3. For this particular f, yeah, they're basically the same thing because this f I can amplify.
Okay, but what is the context in which the 4/9 become significant, as opposed to 12/17 or?
12/17 is more than a half.
Oh, okay, sorry. 6/17.
Well, basically, okay. Let me get back to that in just a second when we talk about the lower bound. Then maybe we'll see. You had a question?
Yeah. So could just be I don't have the intuition. So it seems almost a coincidence that these upper and lower bounds are just match each other. Do you have intuition on why this should be the right answer? And are there other relations and other partial functions f and g where the bounds aren't tight?
Let's see. I mean, maybe also that I will defer to once we see something about the lower bound. I mean, you can kind of see why. Like here, right? I mean, for these particular numbers, right, root n and n, I could have maybe written something else here that also multiplied to n, right? But I think when you look at the lower bound, maybe you'll see why this comes out.
That's fine.
Yeah.
At least the upper bound, you used an algorithm for f which queries n things instead of square root n, which is a bit surprising, I guess. Because you have a randomized algorithm for f with square root n, but you instead use it somehow.
Yeah. Right. Yeah, sure. I mean, you kind of have to play with this, right? I mean, you can't just do the naive kind of composition because that'll give you the naive bound, right? So you kind of have to do something else. Yeah. Okay. All right, so let me say something about the lower bound. Okay, so we actually think about the lower bound again as an upper bound, as designing an algorithm. Okay, so we basically start off with the protocol for F composed with G, and we use this protocol in order to give a protocol for F. Okay, so it's always nice when you can turn a lower bound into like an upper bound. And the basic idea is, of course, we cannot make a query every time our algorithm for F composed with G makes a query, right? That'd be way too many queries. So we somehow need to save on queries. And the key thing is going to be kind of counting what this factor is, by what factor of queries we save. Okay? So the proof of Shalev and Robin, it kind of follows the same framework, and kind of the difference between our proof and their proof is what complexity measure we use here. Okay? Okay, so the high-level idea is, say that we want to compute f of z. So z is an n-bit string here. And we want to use our protocol for F composed with G to do this. So what are we going to do? Well, we're going to sample x1 through xn, where g of xi is equal to zi. So what that basically means is that any output that pi produces on x1 through xn is actually going to be a good output for f on z. Okay. Okay. So that's the basic idea. Of course, the problem with this is how are you going to sample xi, right? Because to sample xi such that g of xi equals zi, well, you have to know what zi is, okay? And that's going to cost you queries, okay? So, so let me just describe this in a little bit more detail with a picture. So imagine that this is a deterministic tree for F composed with G. So again, in designing our algorithm, we're going to use the minimax theorem and design a deterministic algorithm that works for a particular distribution. Okay, so imagine that this is our tree. This is the top part of our tree. And what I want you to think about is kind of the probabilities of going left and right under the following process. So we fix some z and 0, 1 to the n, and we also fix distributions mu0 and mu1 over g inverse of 0 and g inverse of 1. And now imagine this process where I sample xi according to mu zi, and I basically look at the probability over paths induced in this tree, right? So at the root, I have some probability of going left, some probability going right. Here I have some probability going left, some probability going right, etc. Okay? So basically what we want to do is we want to simulate this distribution by making as few queries as possible. Okay? All right, so maybe how you can do this will be more clear here. So let's just focus on this very first query, right, the top query. And now say if g of x1 is drawn from mu0, maybe the probability that x13 is 0 is some number p0. Okay? If x1 is drawn from mu1, right, g of x1 equals 1, the probability that x13 is 0 could be something else, right? It could be p1. Okay? And now I want to simulate this query, which basically means I want to go right with probability p0 if I'm in this case, and I want to go right with probability p1 if I'm in this case. Okay? And I want to do this by just making some fractional query, right? With very low probability, I want to have to actually make a query. Okay? So how can I do that? Well, imagine that p0 is less than p1, and I'm just going to randomly choose r in 0, 1 in this interval. Okay, so if r is actually less than p0, then I can just go left, right? If r is bigger than p1, I can just go right, right? Because I should go right in both of these cases. So actually, the only time I have to query is if R is in between P0 and P1. Okay? So if R lands in between P0 and P1, then I have to actually query, okay, what is Z1? And then once I know what Z1 is, then I know, whether I should go left or go right. Okay, so this is kind of the fundamental procedure that we use in designing our protocol for F, this procedure that we call the bit sampler. So you see that in this case, right, we're not always having to query Z1, right? We're going to have to do it with some probability. And basically the key to computing how many queries we save in this process is to estimate, well, how often is it that we're going to land in between P0 and P1. Okay? So to do this, we define a complexity measure, which we call the conflict complexity. Okay, so this measure is basically exactly what I just described. So we have some distributions mu0, mu1. We have a tree that computes G. And we run this bit sampler routine. And the question is, what is the expected number of times that I can run this bit sampler routine before I have to actually make a query? Okay? And now, as usual, I'm going to maximize over distributions, I minimize over trees, and that's what we call the conflict complexity. Okay? So now kind of intuitively, what you expect is that when I'm running this algorithm for F composed with G, how many times am I actually going to have to query? Well, I'm actually only going to have to query, for every chi of G queries I make, I'm only going to have to really make a real query once. Okay, so that's kind of the intuition. And this is what we're able to show. Okay. Okay, so now to finish the proof, we actually show that conflict complexity is quadratically tight, even for partial G. So there's a randomized algorithm for G with complexity at most this conflict complexity squared. Okay.
There should just be little g on the right also.
Oh yeah, this should be little g, yeah. Okay, and this is kind of the difference with with the measure that we use and the measure that's used by Shalev and Robin. Their measure is called sabotage complexity, and for sabotage complexity, there's actually unbounded separations for partial G. Okay.
What are the pros and cons of using the two measures, sabotage versus conflict?
Well, I mean, I guess using conflict, allows you to extend to partial G. I don't know the relationship between conflict and sabotage, like, which one is greater, but they're both quadratically tight. So.
I think they're used in different applications.
Yeah.
Wait, but here you're saying that there is an unbounded separation between sabotage.
Well, okay, they're both quadratically tight for total functions. Yeah, so the conflict is also quadratically tight for partial functions. Yeah. Okay, so I guess I'm out of time. So I'll finish up. The main open question still remains, right? So say for total functions f and g, what should be the lower bound for randomized composition? Okay, I'll finish there. Thanks.
So maybe
I didn't answer your question. Yeah, go ahead.
No, now I understood. So the reason why you had 4 nines was it was motivated by the lower.
Oh yeah, sure, yeah. Okay, all right, yeah.
No, so your example though uses relations, right?
Yeah.
So it's still even open. I mean, for partial functions, but if both f and
That's
g
right.
are partial functions.
Yeah, it would even be open for, say, f, a function, and g a partial function. Yeah.
So this is sort of suggested in proof bound, like in the randomized case for relations and partial functions. Mm-hmm. Is there something analogous known for quantum complexity? Is the composition theorem only for total functions?
Oh no, I think that also works for partial functions. Yeah, I think there's a paper of Shelby Kimmel that does that generalization. Yeah, relations. Actually, I don't know if if anyone has studied quantumly, but yeah.
In the search problem, it's a very sort of large domain of in-bit domain of search thing. Is there potentially like, is that sort of, I mean, obviously it's in the example.
Right.
Do you have any sense of whether that would be easy to change, or, you know?
Yeah, I don't know. I mean, certainly, you know, as a step towards going to the outer function, the outer problem actually being a function, I mean, one thing you could think of would be to, you know, reduce, you know, the size. But I don't know if you could do that. Yeah.
Do you have a succinct definition of conflict complexity? I suppose this.
Unfortunately, no. So it really is this, basically you fix distributions mu0, mu1. You have a tree which actually computes G, and then basically you run this bit sampler procedure on this tree. And you look at the expected number of queries you have to make before, you know, you throw an R which lands in between that P0 and P1.
And you said you were going to minimize over something and maximize over something else, so there was the distribution over trees, which you obviously get to minimize over.
Yes. Okay. So just like normal distributional complexity, you maximize over distribution, you minimize over algorithms. Yeah.
Can you give some intuition why? So this is, it's open for the randomized case, but we know it for the quantum case.
Yeah.
Which might imagine to be harder. So.
Right. Actually, the quantum case just behaves so nicely. So the reason is because in the quantum case, we have this lower bound technique, the adversary method. And this method, you know, it's like you can write it as an SDP, so it's kind of a, you know, nice object. And it just characterizes quantum query complexity even for partial functions. And so that's Reichhardt's result. And so, and you can show that this SDP perfectly composes, you know, and kind of the natural thing, right? For one direction, you take solutions to the primal, you compose them. For the other direction, you take solutions to the dual, you compose them. So that's why, you know, randomized, we don't have a nice lower bound technique, which we know that characterizes, or randomized query complexity, right? That we could kind of use in the same way.
Do you have another distributional version of this conflict complexity? So if you apply the minimax, you might expect to get something not of this form.
Wait, say again? What?
So in some other cases, you apply minimax and you get, instead of something distributional, you get some worst case measure.
Oh, so what is the worst case version of conflict complexity? The good question. I don't know. Yeah, you should get some measure there. I don't know what it would be. Yeah.
So this is just a comment.
Okay.
So if you look at the NAND tree, the NAND out tree.
Right.
So Mike and I, we have this lower bound for that particular problem. But I think that may be a sort of a good sanity check for how these kinds of techniques work, because this is something that Mika and I had worked on in the context of communication complexity. But we had to prove something for conical Hunter degree.
Right. A composition,
It turned out to be a nasty problem.
Right.
And the hope is that some techniques like these would actually, you know, circumvent all of that.
Right.
But I think it's a very good candidate for testing whether the composition theorem actually works.
Right. And also for things like recursive majority of 3, right? The complexity is still open.
Right.
So, yeah.
But that at least recursive majority
Yeah.
would seem to show that, I mean, there are functions where you don't get a perfect
Right.
product.
Yeah.
Yeah,
Composition.
You mean like the top-down?
What's that?
You mean like the top-down type of argument for recursive majority of 3?
Well, I'm just thinking, just take majority and two-level majority.
Right.
Right, so that's the composition of majority with itself. And I think that's going to show that,
Right.
because there is an advantage you get over two
Yeah, but it's just like a constant factor, right? So.
I think you have this notion that there's a directional algorithm and that's not optimal, right? Is that what you're referring to? That might be your case.
Yeah.
I think you have to be careful, right, when you talk about these things that are composed many times, because you could still have a composition theorem that's just off by a constant factor, right? But once you iterate that d times, then that becomes a factor of like 2 to the d or something.
So do we know how does the complexity compare to block sensitivity?
Yeah, so that's kind of my other open question. So to be honest, we didn't really look into any of these things, so we just kind of used conflict complexity for this one application. So actually, I don't know how it fits in the pantheon of complexity measures. Yeah. Okay.